Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're happy to have James Lee tell us about discrete differentiation and local rigidity of cuts.
All right. Okay, good. Okay. All right, so so I'm going to talk about, well, as you've all said. So thanks for coming, even though some people didn't even know there was a talk, so it's even more miraculous that you ended up here. All right, so here's a brief outline. First, I'm going to talk about optimization over cuts and how this is related to some classical combinatorial optimization problems. And then I'll talk about the relationship with metric embeddings. And then I'll introduce sort of discrete differentiation as a technique for analyzing these embeddings. And finally, the last part of the talk will be about sort of the main technical issue that arises from a particular construction, which involves local rigidity of cuts in the plane. Okay, so this is the basic outline, but let's start at the beginning. So the first thing is to understand sort of what is the cut cone. So if you just have a finite set X and a subset S, then one can define this cut pseudometric associated to S as a function from pairs of points in X to 0, 1, which is just sort of 0 if the 2 points are on the same side of the set and 1 if they're on different sides. So 1S here is the characteristic function of S. So in case that wasn't clear, here's a picture. Here's X, here's a set S. If we take a bunch of points, then sort of the pseudometric associated with S assigns distance 1 to this pair of points and distance 0 to this pair of points. Okay, good. And now the cut cone is just the cone generated by all of these pseudometrics on the finite set X. So the cut cone on X is the set of all non-negative combinations of these things. So you can consider these things as lying in R to the X cross X, and then the cut cone is the cone generated by all these objects. So let me just give a slightly different way of saying that. A mapping D from pairs in X to real numbers is in the cut cone if and only if there exists some measure on subsets of X such that, okay, so I'm thinking about this as a distance because eventually it's going to be, so such that the distance between X and Y is exactly sort of this non-negative combination here. Okay, so I just said what it means to be in a cone. Okay, again. Okay, and so one thing that's going to be sort of very key to this talk are sort of cut measures, so measures on cuts. So for instance, here's a picture of 3 cuts, each has a non-negative weight. This induces so this measure on cuts induces a distance given in this way. So for instance, the distance between these 2 points is what? 3.4, right? Because 1.4 plus 2.0 is 3.4, and this is 5.5, and so on. Okay, so from every cut measure, we actually get a distance in this way. All right. So if we could optimize over this set, that would be awesome. So for instance, if we have a graph, then we can express the maximum cut in G as some sort of linear, it optimizes some linear function over these distances, subject to D being in this cone. Okay, so if we could optimize over this cone, that would be awesome. We could solve problems like max cut. Okay, but of course, max cut is NP hard, so we don't expect to be able to optimize over this cone efficiently. So then this leads to the notion of relaxation, which is we take some kind of bigger cone that contains the cut cone, and we would like to be able to optimize over this bigger green cone. And then sort of the idea of an algorithm would be, well, first let's optimize over this larger convex set, and then do some kind of rounding where we take a point here and try to map it to a close by point in the original set. And this way we recover a cut. Okay, so now I want to talk about what does it mean for 2 of these points to be close together. I mean, of course, whether 2 things like in this cone are close depends on what you care about. A nice way to think about this is that all of these things are trapped inside the metric cone. So this big pink thing is the metric cone. This is a set of all symmetric functions that satisfy the triangle inequality. So in particular, the cut cones produce distances D that satisfy the triangle inequality, and everything we'll think about today is going to sit inside this metric cone. And that means every time you see a red dot, that's just going to be a metric on the finite set X. So all the red dots are metrics. They give different geometries on the set X. And then once you think about these as geometries, you can look at geometric ways that these 2 spaces might be similar. Okay? And the most sort of natural one is, well, 2 spaces are close, like the L infinity notion, if all the distances in given by one metric are similar to all the distances given by another metric. Okay? So this leads to the notion of bi-Lipschitz distortion between two metric spaces. So if we have a map between two metric spaces x and y, the Lipschitz constant, or I wrote here the expansion of the map, is, well, the maximum by which distances are expanded. The contraction is the maximum amount by which distances are contracted under this map. And then the distortion of the map is the product of these two things, the product of the expansion and contraction. This is a scale invariant way to measure how much this thing changes distances. So that if, right, okay? And then this notation won't actually be used except in one place, so it's not so important. But C sub y of x is the smallest distortion with which we can embed x into y. So we look at all the ways to embed x into y. The one which induces the smallest distortion gives us cy of x. Okay, so this is one kind of notion for comparing 2 points. We have two metric spaces. We can ask what's the distortion between them. And this wasn't all for not. So, okay, I have one more sling. So I didn't tell you what this green cone is going to be yet. So this blue cone is the set of cut metrics. And I didn't tell you what we're going to be talking about our efficient relaxation as. So so here's something well known. It's not very difficult to see. Cut metrics on a finite set, you can also think of as L1 metrics. So they're the same thing. So a metric space here in the cut cone is in the cut cone, if and only if there's an isometric embedding to some finite dimensional Euclidean space such that the distance is exactly the L1 distance. So that's okay. That's a different way of characterizing the cut cone. That's an exercise to see that. And what we're going to talk about as this sort of larger convex body is a set of negative type metrics. And I'll mention later on why this is very natural. I mean, first of all, this set is such that we can optimize over it efficiently. So it's going to be, that's one reason to care about it. But there are also lots of other reasons to think about it. And you can talk about this set as being the set of metric spaces which admit an embedding into Rn, but now such that the distance is the square of the Euclidean distance. Okay? And okay, so it's not completely clear that that sort of the negative type metrics contain the L1 metrics, but again, I'll leave it to you as an exercise. It's a simple exercise, but okay, but these negative type metrics, these are the squares of Euclidean distances, okay? And so this is so now if you set this up in our languages before, we're looking at sort of like, given some metric space here, how far is it from a metric space here, okay? Okay, and what I want to say is that that's not just sort of like, that's an interesting structural question, but it's actually tightly connected to optimization problems. So let me tell you an optimization problem. So the sparsest cut problem on graphs is just the following. We have a set of vertices. We have a set of edges. Okay, that's our graph. And we also have another set of edges, the blue edges, which are classically called the demands. And then in the sparsest cut problem, the goal is to find a cut in the graph, which minimizes this ratio. So it minimizes the fraction of red edges cut to blue edges cut. This is the general sparsest cut problem. If, for instance, these blue edges were just a complete graph, if they were everything, then this objective is exactly the conductance of the cut.
You want to bound on the size of x. So supposed to be over 2.
No. Here it's symmetric, so it doesn't. It's not going to matter. So I mean, for instance, if this is the complete graph, and this is going to be the product of S and the complement, and the product of the size of S and the size of the complement. So So this is the sparsest cut problem. As I said, it's a generalization of, for instance, conductance or expansion, which is the case when you just take D to be V cross V, the set of all pairs in the graph. Okay. So here's something cool. Okay, so this is a problem. You can write this down as an optimization problem over cuts, and if you relax it to an optimization problem over this negative type cone, it turns out that the integrality gap for endpoint graphs. So in other words, I look at this problem. I look at what's the furthest the objective can be when I optimize over cuts versus optimizing over negative type metrics. The integrality gap for end vertex graphs is precisely the worst distortion to embed one of these metric spaces in one of these metric spaces for endpoint metrics. So the question of studying how far apart these two cones are is actually exactly equivalent to the problem of determining how well this algorithm does for sparsest cut. Okay, so it's one. So that gives a natural reason for studying it. And in fact, it was so natural and apparently like compelling that in '94, Goldman and Lineal actually conjectured that these two cones are very close together. So they conjectured that every negative type metric on a finite set can be embedded with some universal constant distortion, independent number of points, into a cut metric. So they conjectured that for every point here, you can go here and only lose some order 1 in distortion. Okay, so very well, I'm going to talk mostly about lower bounds. Let me mention that the best upper bound is due to Aurora, myself, and Asaf Naor, which is that for endpoint metrics here, you can move into the cut cone, but you pay something which depends on n. And that something is square root log n times log n, which is the best known bound. This sort of goes back to work of Bourgain in 85, 20 years, now 25 years ago, but which gave an order log n bound, and then a sequence of works, and many works eventually give you this bound. I'm not going to talk about this. We actually saw something stronger, which is related to some problems in nonlinear theory of Banach spaces. But let's ignore that for now. Okay, so because I'm actually going to introduce one more object. Okay, so we have the negative type metrics, we have the L1 metrics, and now the last thing we're going to need is something that I call soft negative type metrics, and I'll tell you now why they're interesting. So this is the set of metric spaces where you can't get the distance exactly equal to the square of Euclidean distance, but up to constant factors equivalent to the square of Euclidean distance. So maybe, okay, so I mean, there's a constant, there's an implicit constant that I haven't listed here, but maybe the distance is at most 10 times the squared Euclidean distance and at least the squared Euclidean distance. So this is sort of like, up to constant factors. And the reason that this is important, we'll see a structural reason in a moment, but even from an algorithmic perspective, all the known rounding algorithms, so all the algorithms which use optimization over this green cone and then round to this L1 cone, actually only use the weaker condition that you're inside this soft cone. They only use this weaker condition. And that's actually been crucial for a number of algorithms that try to do things faster. So if you don't want to solve a semi-definite program to get your point inside this cone, you can do something faster, like work of Sherman, who gives sort of n to the 4/3 time algorithm for approximating sparsest cut, uses the fact that actually the optimization occurs over this larger set. That turns out to be important for designing fast algorithms.
It's still a metric, right?
What's that? It's still a metric. So everything is inside the metric cone. So every point thing is, but now it doesn't have to be exactly a squared Euclidean distance. It can just be close to one. Okay. It doesn't seem like such a big difference, by the way. So I mean.
So by definition,
So here this is really a metric. Okay, so I mean the squared Euclidean this is really a metric. We don't lose any constant in the triangle inequality. It's just that so it depends. If you pass to the equivalent Euclidean squared distance, then it's no longer a metric, right? But it's so if you mean by pseudometric that you lose a constant in the triangle inequality, that's true. But that's actually a very weak property. You have a much stronger property if you pass to this, which is that you only lose, even if you apply the triangle inequality to a path of length 100, you still only lose the same constant.
So is it equivalent to saying I look at all metrics that can be embedded with constant distortion into negative?
No. So this is an interesting, right? So this is interesting. In fact, the question. So you can ask that what's that if I have a point here, how far do I need to go to get it to be here? And well, I'll talk about it at the end of the talk, but it's a non-trivial question. So okay, right. So it's possible that in order to deform this metric so that it's actually negative type, you need some huge distortion. Even though this is only by a constant, somehow it's a little bit.
Is it true that this is actually a cone?
Well, if you write it, yes. If you write it the right way. Yeah, so if you write it how I said it, then it's a cone. It's just a bunch of, the distances d give you a bunch of positive semi-definite constraints. Okay. All right, so now jumping ahead 10 or 15 years after the Gomez-Lino conjecture, it was a huge result related to lots of other things, including unique games conjecture, when Colt and Vishnoi proved that in fact it's false. And they showed, in fact, some quantitative bound, well, Colt Vishnoi combined with the follow-up work, okay, so there exists, endpoint metric spaces of negative type, which, in order to move inside here, you have to pay something. It's a slowly growing function, but it's something. So it's not a universal constant. And I want to stress something about their proof. Their proof works in the following way. First, they exhibit one of these soft negative type metrics, and then via by the time they proved it, sort of rather standard techniques from complexity theory illustrate that this metric is far from the cut cone. And then the really sort of interesting magical part of the proof is this part, where they show that this point is actually close to a real negative type metric. So they answer Nikhil's question for this particular space, that sort of, you can actually just pay a constant and move inside this negative type cone. I still claim that this is not very well understood. I don't know if Naor disagrees with me, but this is a rather magical kind of thing where they sort of like, based on faith, they do something, and then they have 3 pages of technical calculations that verify that it was the correct thing to do. But it's still, the motivation is still kind of like faith for why you can do this. Okay, so now, back in 2004, when Asaf, Naor, and I saw this, okay, so yeah, this is blinking because it's the magical step.
Does that show that any metric over there was it a particular?
No, this is their particular metric space and a particular kind of perturbation that applies only to their metric space. Well, it's been generalized slightly, but to sort of families of the same kinds of things. Okay, so Asaf, Naor, and I saw this back in 2004, and we said, okay, can we try to do something? Like, let's copy their sort of approach and try to do something better. So in other words, let's try to find some soft negative type metric and then, show that it's far from here and close to here. And okay, so a very sort of general theorem in this regard is that every doubling metric space is actually soft negative type. So this is a theorem of Aswad, which I have essentially, corrupted by writing it this way. But a doubling metric space is just one where has some kind of finite dimensionality property. Every ball can be covered by order 1 balls of half the radius. Okay. So this says, okay, well, let's look for a doubling space. This will automatically be soft negative type. So the question of whether there is a doubling space which doesn't embed into L1 is the sort of an interesting question. And for various reasons, this is the most natural thing to try. In particular, because Aswad himself had originally asked whether every metric space embeds into a Hilbert space, which is more restricted than embedding into L1. And this was the first counterexample to that question. So what did I say? Every metric space? Okay, so that's also false, but well, it's not so simple, but sorry, not so simple, right? Okay, if you want bi-Lipschitz, it's not so simple. Okay. In any case, all right. So then sort of so now we've started looking at this. I'll tell you in a second briefly about this, although I'm not going to focus on it. This 3-dimensional Heisenberg group, and before I tell you about it, I'll just tell you sort of what we proved. So so by Aswad's result, this point sits here. Great. We spend a lot of time to prove the difficult part of the Kolt-Vishnoi thing, which is that you can move it inside this negative type cone. Okay, and this is again magic. It's like I'm not going to tell the story, but the story is like kind of magical, and then you get like 7 equations, one of which might work, and you plug them all into Maple, and then Maple says that only one of them could work, and then you check it and it does, like this kind of thing. Okay, and it uses very strongly the analytics, the fact that sort of the analysis you can do Fourier analysis on this Heisenberg group, and it interacts very well with the geometry. So we did this magical step, but then, although we had reason to suspect that it doesn't embed into L1, we didn't know how to prove this. So we did the next best thing, and we conjectured it. We conjectured that the Heisenberg group is far from this L1 cone. Okay. All right. So then it took essentially 3 years for Cheeger and Kleiner to prove that it's true. So they proved that in fact the metric I haven't told you about. It's just the Cayley graph. If you just take, for instance, the group of 3x3 upper triangular matrices with integer entries and take some Cayley graph there, that's the metric that we're considering. They proved that metric doesn't bi-Lipschitz embed into L1. And one reason that was very interesting is because it was clear that the way you should prove it is via a differentiation. I'll talk about differentiation in a second. But no sort of straightforward theory of differentiation can hold for L1 valued mappings. So this is actually a big problem in the nonlinear theory of Banach spaces. Like, what does it mean to differentiate L1 valued maps? So the fact that they were able to solve this question, and give a reasonable answer in the setting of the Heisenberg group was very nice. Okay, so they solved this, but it doesn't give a So this shows that you can do it with a constant, but it doesn't give a quantitative bound yet. Okay. Let's see. So we started late. So let's just ignore the geometry of the Heisenberg group. No? You don't want to ignore it? All right, okay, so I've already said what the Heisenberg group is. You can endow this with well, if you think instead about forget the real case, think about integer entries and think about the Cayley graph, then here's what the structure of this space looks like. Okay, so in the Cayley graph, and then I'll tell you about the continuous case, but in the Cayley graph, you can take 4 generators here. I'm not going to write the generators down, but you put a 1 here and zeros here, and you put a 1 here and zeros here. Okay, you put plus minus 1 or plus minus 1, and that gives you 4 generators. And you can think about those generators if you embed this in the natural way, in fact, according to the lettering I gave it here, into R3, you can think about the generators as sort of moving in the x direction or the y direction. And the way that you move in the z direction is you use the fact that the group is not commutative. So if you go x, y, x inverse, y inverse, then actually you increase by 1 in the z direction. Okay, and there's actually a continuous version of this space where, in order to go distance, say a, in the z direction, you actually trace out a circle of area a in the xy plane, and when you trace out the circle, you go up 1 in the z direction. So it's if you look at the continuous case, then you sort of here's a picture of what's going on. At every point, you're only allowed to move in a 2-dimensional plane. But the orientation of the plane changes as you move. And actually using that, you can connect any 2 points by a curve that only at any point only travels in these 2-dimensional planes. And the reason essentially it doesn't embed into L1 is because, okay, so it's basically because infinitesimally all movement is horizontal. And if you think about what that means, it sort of means that the cuts in the embedding should be perpendicular to the direction of movement. That'll make more sense. I'm essentially giving this explanation for Yuval's sake because you wanted to hear about the Heisenberg group. That'll make more sense in a few slides. So all the cuts should be sort of perpendicular to the direction of movement. And then if you sort of look at what that means, it basically means that the cuts have to be sort of vertical in this space. That's not exactly true. They just have to be vertical locally. We'll get to that in a minute. But that means that sort of points which are vertically separated collapse in any L1 embedding because most of the cut measure is focused on cuts that look like this, which don't separate points like that. If you don't know what okay, so in a second I'm going to give a construction which does this, but in a simpler way, so then it will all make sense. That's the Heisenberg cube. It's beautiful. But, also the geometry is quite difficult to work with. So, like for instance, to connect pairs of points is non-trivial. Even to see that the space is connected, the continuous space is connected is a theorem. Okay. But let me tell you what I'm going to present today, which is, yeah.
You said it was used earlier as a counterexample to what?
It was used as a counterexample to whether a doubling space bi-Lipschitz embeds, so with order 1 distortion, into a Hilbert space, into L2. So even into Euclidean space, it was known. Does every doubling space admit an order 1 distortion mapping into a Euclidean space?
Did they use that vertical separation property there too? Or?
No. So there what you do is you use. Okay, Yuval likes the. So there. Okay, so you take a map into L2, and the idea is that so this map is if this map has is small distortion in particular, it's going to be Lipschitz, and then since it's Lipschitz, there is a whole theory of differentiation for maps that take values in Hilbert space. So in fact, differentiation means that since this map is Lipschitz, locally it can be approximated by a linear map. So a linear map in this setting sort of means that, for instance, F, G, H, these are 2 matrices, should be, let's not use F, let's use L for linear map. Should be LG plus LH. Okay? So using differentiation, which I'll talk about in a moment, you can say that locally this map is approximated by a linear map. But now a linear map, on the one hand in Hilbert space you're commutative, and on the other hand over here you're not commutative. So here's something that follows from having a group homomorphism from H3 into L2. It implies in particular that L of GH equals L of HG, right? But these 2 points are different in the Heisenberg group. If you take 2 points which are sort of like any pair of elements that don't commute, these 2 points are different. So locally this map is going to map them to the same point in the Hilbert space. Okay? So okay, so that was a bit vague, but the point is that when you're taking maps that have values in L2, this sort of differentiation theory, the fact that you can approximate a Lipschitz map locally by a homomorphism, works out very nicely. Okay, there's like when you change the target space to L1, everything goes away. So even if you take a map from the real line to L1, which is Lipschitz, this map can be differentiable nowhere. Whereas if you take a map from the real line into Hilbert space, it's differentiable almost everywhere. So Lipschitz map from real line to Hilbert space is differentiable almost everywhere. So this group was used to prove that doubling spaces don't embed to Hilbert space, but the method by which the proof goes completely breaks down for L1, even at the very start. So the very start is to consider maps from the real line, and even those get killed. So there are even isometric embeddings of the real line into L1, which are differentiable nowhere. It's easy to produce them. Okay. We'll see an easy differentiation argument in a moment. But here's what I want to prove today. I want to prove a nearly tight separation between this soft negative type cone and the metric cone. Okay? So there is the upper bound I mentioned before holds. So there is a square root log n upper bound for points for going from here to here. And I want to prove that like this strong quantitative result that actually that's tight. So these two things are really separated by square root log n. Yeah.
What's the metric on the input group?
On this group?
The distance?
On here?
Yeah.
On the Heisenberg group? Yeah. So the metric here is hard to explain. If you want something which, for all intents and purposes, except for the proof, is the same, you can consider the group of upper triangular 3x3 matrices. So consider the group of these things with integer entries. X, Y, Z are all integers. And then the generating set is just plus minus 1, these things, and also these things. So this is a graph, a Cayley graph. Just take the shortest path metric. That's the metric on this Cayley graph with these generators. I mean, you can take any generators you want, but right. So in fact, this embeds isometrically, yes, into this version. This is sort of a continuous version of that space, but it's important for the proof that you're in the continuous version. It's unknown how to do the proof in a discrete version, and it's in fact unknown in a strong way because certain things would be much easier if you could do it in a discrete setting. Okay, this is what I'm going to try to prove today. That we can get sort of an optimal separation here, and then at the end which is going to be in 20 minutes, I'll talk about whether you can get sort of an optimal separation here. But this is going to be based on a discrete differentiation theory. So let me tell you now about that, and then I'll tell you the formal statement of the result. Okay, so we've already talked about it, but let's just remind you what it means to take a derivative. So Lebesgue's differentiation theorem, for instance, says that if you take a map from the real line to the real line, which is Lipschitz, for instance, then almost everywhere you can approximate this map by a linear map, right? Almost everywhere the map is approximated by its sort of tangent line up to sublinear error. This is sort of what it means to take a derivative. And now, in the last 40 or 50 years, sort of generalizing this to spaces with less and less structure has been very important in Banach spaces and in geometric group theory. So I'm going to follow an approach taken by Eskin-Fisher and White, which is discrete. Okay. So here's sort of so let's just remember what we need. The two interesting facts here are sort of we get a locally linear approximation, and we get it almost everywhere. So we're going to now lose all the structure and have to replace linear by some other property and almost everywhere by some other property. Okay, so let's just look at a path of length n and a metric space x. And now first let's look at what it means to be linear. So here's a very sort of interesting elementary way to say that maybe this map from the path to x is linear. If the triangle inequality for this path is tight up to a 1 plus epsilon factor. So if I apply the triangle inequality, it of course says the distance between the endpoints is at most the sum of the distances along the edges, and that's the other direction. And so I'm saying now the triangle inequality is actually tight up to a 1 plus epsilon factor. Okay, so just as a picture, here's the path, right? This map is pretty efficient. This map is somewhat less efficient, right? Okay, so this is the notion of efficiency. All right, and now we need a notion of almost everywhere, but we're in a discrete setting. So almost everywhere is going to have two components. First of all, there's going to be like a locality, but also a granularity. So it's going to be local, but also some kind of coarseness. You can't look too, you can't look too closely at the line. So okay, so what I mean by that is, okay, so there's some granularity parameter. So let's say the granularity here is 4, because there are 4 points. Okay, this is, I'm just going to show you the localities and hopefully you understand. So this is one locality, these 4 points. Okay, here are 3 other localities at the next scale. Here's a locality, here's a locality, here's a locality. It's sort of, it's a scale, but also sort of, I'm only allowed to look at, these 4 points. In other words, if I was considering, for instance, some map on this space, then I couldn't see what the map does in here at this locality, and so on. So now here are 9 localities at the next scale. Okay, and now here's a theorem which is fairly easy to prove, which is that if I have a map from the path into a metric space and it has distortion D, then it's epsilon efficient almost everywhere, as long as the path is long enough. So as long as I have enough scales. So you need number of times you need to subdivide is about D over epsilon. So if M is the granularity, then you get like M to the D over epsilon points. Okay? And by the way, here's the proof. And I said, what does almost everywhere mean? It means that if you choose, I'll give you a measure on localities. Choose a random scale and then a random offset. So that's the measure. Almost everywhere. There's another parameter delta, which I haven't put here, but you can sort of get it for, if you want, you can get it, for instance, for 99% of localities, you can get this property. And here's the proof. I'll give you the proof. So let's just do the proof. Let's just find one locality at which it's epsilon efficient, and then it generalizes easy to finding many of them. Okay, so here's the proof. Okay, so if our map is efficient at this red scale, then we're done. We found one locality. If it's not, then it has to be inefficient. It has to look like this. Okay. So now I say, okay, well, I'll look at the green scale. I'll look at these 3 localities. If it's efficient on one of these, then I'm done. Otherwise, it has to be inefficient on all those scales. And okay, I can do the same thing again. And you just see that, the more times you go, the longer and longer this curve is going to become in the target. And so eventually you're going to violate your distortion condition, because this curve is going to have some fractal structure at all scales. It's going to be too long. Okay, so that's the proof. Very simple. All right. So now the key is to specialize. So we have our locally linear property. We have almost everywhere, and we have a differentiation theorem. And now the key is to specialize to the target space being L1 and see what happens. Okay, and so this was done independently in joint work with Raghavendra, and also in a later paper of Cheeger and Kleiner, where they gave a different proof for the Heisenberg group. But here's the idea. If we take a map from the path into L1, okay, so remember, this just means that we take a cut measure on the path, and the distance is given by, the distance between points is the measure of cuts that separate them. Then I claim this map is 0 efficient, so the triangle inequality holds exactly, if and only if the cut measure is concentrated on cuts which are half lines. So if and only if the only cuts that occur are half lines. Okay? So this is a good cut, this is a bad cut. And in fact, you can see that this cut is not efficient. The distance in this cut between the endpoints is 1, but if I go along the edges, I count 3, the distance is 3. Okay? So that's the exact version. And now sort of the almost version is that, which just follows from exactly what I said, is that a map is epsilon efficient if at most an epsilon fraction of the cut measure is supported on these bad cuts. And all the other cut measure has to be on good cuts. Okay? So then what the differentiation theorem says is that if I give you some map from the path to L1, which has small distortion, then there exists a locality such that when I look at the cut measure restricted to that locality, most of the mass is on these monotone cuts, these cuts which are like half lines. Okay? Good. Okay, so you can use that to solve some problem from Gupta-Krauthgamer-Lee and Sinclair. Let's ignore that. Okay, and now let's try to use this to give some quantitative bounds. Okay, so the first thing is that 2 years ago, Cheeger, Kleiner, and Naor proved a much stronger bound than log n. They showed that for the Heisenberg group, for some delta, you can get the distortion to go like log n to the delta. But delta is like 2 to the minus 1,000, and the paper is like 90 pages long. So okay, so that's, so you don't have a lot of hope that you can get delta equals half, at least at the moment, from that kind of analysis. So what I'm going to present now is a doubling space which gets almost the optimal bound on square root log n as a lower bound. So So okay, so I mean, it says that now we have some techniques to get in the right ballpark of the correct asymptotic bound. Okay, so I'm going to go to like 425. Is that okay, Yuval? All right. Okay, so now in order to do that, we just have to bump up our differentiation theory by one dimension, turns out. And instead of thinking about lines, just think about squares. Okay. So again, let's consider the unit square in the plane. Consider some cut measure on the unit square, which comes from an L1 embedding. And now I can ask the same question: if this cut measure gives me a metric on the unit square, which is order 1 distortion, say from the Euclidean metric, what does it imply about the structure of the cuts locally? Okay. And the result that you get is that when you zoom in locally and you look at the cut measure on some tiny copy of this square inside, almost all the cut measure is concentrated on half-space cuts, so intersections of half spaces with the unit square. Okay, and the reason for that is just that instead of differentiating along, we differentiate along paths, but instead of differentiating on a single line like we did before, you just differentiate along all the Euclidean lines. So you differentiate in all directions, and the only cuts which are monotone with respect to all the Euclidean lines are the half-space cuts. Right? Basically, whenever I hit this square with the Euclidean line, if I have a cut such that whenever I hit it, I cross the boundary at most one time, that cut has to be a half-space cut. Okay? So the half-space cuts are sort of the only cuts that are stable with respect to differentiating along all the Euclidean lines. Okay, so we're going to use this property now, and here's the construction. Okay, so that was great, but this square embeds isometrically into L1, so it's not so interesting. We have to do something a little bit more. So here's the basic step of the construction. Take 2 copies of the unit square and identify their boundaries. So just glue them along the boundary. So topologically, we get a sphere. Geometrically, it's not a sphere. Geometrically, if I take 2 points in the top copy, the distance is the Euclidean distance. But I just want to take the induced path metric. So if I take, for instance, a point here and a point here, the way to go is sort of like, okay, go to the boundary and then go. So it's not the sphere metric. It's the, on each copy you have the flat Euclidean metric, and then you move between them in the obvious sort of way. Okay, but let's suppose I have an embedding of this. What's that?
What do you call it? The pillow case.
Well, right now, okay, well, yeah, we'll see in a second. So you can think about it as a pillow. Yeah, even then it's warped. It's a very flat pillow. in some sense, the reason that it's difficult, you can't represent it because that's what we're gonna anyway. Okay, so. Okay, so suppose you take some embedding of this glued sphere into L1, and just suppose for the second that that the cut measure sort of resulting from the L1 embedding is supported on cuts which are monotone on both the top square and the bottom square. Okay, so I take an embedding, and if I look at the cuts in the embedding, when I restrict them to the top square or the bottom square, I see monotone cuts, which are exactly intersections of half spaces with these things. Okay, so what does it mean? Well, take any such sort of a cut, look at what it looks like in the top copy. It looks like this. Now they're identified along the boundaries, and it's easy to see that any half space intersected with the unit square is determined by its intersection with the boundary. So the cut has to be the same in the top and the bottom, and therefore, if I consider any 2 points which are vertically separated, so the same point but in different copies of the 2 squares, such a cut cannot separate them, right? So what it means is that if I take a mapping from this sphere to L1, where all the cut measure is on monotone cuts, and then it has infinite distortion because it collapses vertical pairs. Okay. So now we want to. Of course, by the way, there exists there exists an embedding with something like, the standard sphere is a square root 2 distortion embedding of this thing. So of course, there exists a good embedding. They don't have to be supported on monotone cuts. But now the idea is to construct a space where, for most of the spheres, the embedding has to be supported on monotone cuts, and then it will have to collapse them. This is the idea. Okay. So these are the diamond folds. Okay. So we start with the unit squares before, and now. Okay, and this is the sphere, but I've drawn it so there's 2 copies here, one a top copy and one a bottom copy. But I've drawn it in a way so that it has 8 squares which are up to scaling isometric to the original square. So now I have 8 more squares. And what I'm going to do is just apply the same thing to each of those 8 squares. So I glue another square onto each of them. And I get some picture like this. And then I want to keep going. So the idea is that basic operation is you can take a square and then do this pillowing thing. And then once you do that, you have 8 sort of smaller squares, and now you pillow each of those and you keep going. You get some recursive construction like this. Okay, so this is like some kind of recursive bubble wrap or something. And the main important property is that no matter where no matter where I look in this space, at every scale, I see copies of this sphere. There are copies at the big scale, copies at the next scale, and so on. Okay. And so in fact if you want to just prove that this thing requires that there's no bi-Lipschitz embedding, you can, like, if you want to pass to the infinite version, eventually I want a quantitative result. We're not going to go to the infinite version, but pass to the infinite version, you can prove there is no bi-Lipschitz L1 embedding just by saying you apply the differentiation argument, and that says there must be some sphere where almost all the cut measure is supported on monotone cuts on the top and the bottom, and then all that cut measure collapses vertical pairs. There's only epsilon fraction left to separate the vertically separated points, and now send epsilon to 0. So there has to be there has to be a sequence of vertically separated pairs that get worse and worse and worse. Okay. All right. So now, okay, good. So now I want to talk about the quantitative bound. So again, the result is actually that you can take the infinite space. The claim is that there are actually endpoint subspaces of there, such that you get some very strong quantitative bound on the distortion of those endpoint subspaces. And in fact, if you really don't, eventually you don't need the continuous structure. Again, is important for the analysis, but you can just take the graphs that form the one skeleton of these spaces, and that's enough to give the bound. Okay. Okay. So now, what's the quantitative problem that arises here? So it's the following: you take the unit square, and you take a set. And now, if I tell you that every line crosses the boundary of the set at most once, so we don't count the boundary of the square as the boundary of the set. So these crossings don't count, but this is the boundary on the inside. So if I tell you that every line crosses at most one time, this line doesn't. This line crosses twice. But if every line crosses the boundary of S at most one time, we've already said S has to be the restriction of the intersection of a half space with the unit square. Okay. So now, if you want some quantitative version of this theory, you have to start asking about a slightly more difficult question, like what if 99% of the lines cross the boundary at most one time? So now I have a set where most lines cross once, but of course any line that goes through this dot crosses twice, and any line sort of at this bad angle crosses twice. So you can ask that question, right? And the goal would be to say that, for instance, in this case, the set has to be close, say, in symmetric difference to a half space, right? But in fact, for the discrete version, it's even harder. We actually only have a finite set of points along these lines. And now you only get to see a crossing if it's witnessed by this finite set of points. So for instance, these points witness the crossing because they're not in the set, not in the set, not in the set, then in the set. But these finite set of points along this line don't witness this spot at all because they totally miss it. So, okay. And so the goal is to, and this is dictated, the fact that we have to take a finite set of points is dictated by the fact that we want a quantitative bound. So let me just tell you the main quantitative sort of theorem that comes up there. It's the following. So take the unit square and take some subset, and then choose a random line L, so from like the kinetic measure. So just a random line L conditioned on intersecting the unit square, and choose k random points on the line. Okay? And now let theta sub sk be the probability that this random line with random points sees more than one crossing. Like it crosses into S and then back out of S. Okay? So the main technical theorem is that there exists a half space such that the symmetric difference between, I didn't take the intersection with the square, but the symmetric difference between S and the half space is only square root of theta, plus something that depends on the granularity of your sort of ability to look at the space. So as you take, there's some error term that depends on k. It's actually not clear whether this is necessary, but it doesn't matter so much for us. And in fact, and this is odd, I didn't expect this. This square root is responsible for the square root in the square root log n. And this is tight. So as you can see, for instance, if you take this set, then the area of the symmetric difference to the closest half space is about delta. You pay the area of this triangle up here. But the probability that you detect it is only delta squared. And the reason for that is that in order to detect this bump, the line has to be sort of within this within this shift of which has only measured delta, but also the angle has to be correct, which is also another delta. So you get probability of detecting it's a delta squared, and the symmetric difference is delta. So in fact, this square root dependence is tight. And it's very strange that, it's very strange that somehow that's a two-dimensional phenomenon. It's very strange that gives the correct bound. I always thought that the correct bound would come from the differentiation theory, and then, so it's just strange to me that this comes from sort of like two-dimensional, some very strong, seemingly strong two-dimensional property. All right, I don't know what it means. So now to conclude, let me just say, so what we've shown is a gap between this soft negative type and L1. And what we really want to finish the entire question is a gap between actual negative type and L1. So what we need is sort of, we need one more of these magical steps. There's the Kotvishnoy step, there was the step for the Heisenberg group. And so usually when you have and both these were kind of miraculous, and the proofs are relatively opaque. So you can ask, usually when you have miracles, there's some reason behind them. So for a long time I thought it should be the case that, as Nikhil asked earlier, that every point here should be order 1 from this thing. This was just sort of, there's a special proof for each of these two cases, but there should be some more general property. But in fact, it's false. So with my student last year, again using differentiation, we proved that there is actually a substantial gap between soft negative type and negative type. Which means in particular that that sort of closing the, getting our construction to give the optimal integrality gap for the original semi-definite program is still a non-trivial open problem.
Do you know whether this is tight, or is there anything non-trivial with the same one?
Like the upper bound? So there is an improvement to 1/3, but you can get a lower bound of log into the 1/3 by analyzing our construction slightly better.
No.
Upper bound is not log.
The upper bound is square root log n.
Which is?
Which one? The 1/3 or this? This has appeared.
But that's appeared in the 1/3 hasn't.
I agree. It's unclear whether the 1/3 will appear. No. The 1/3 is like okay. It's also not the right answer. The right answer is probably square root log n. So. If you would like to encourage my student to write the 1/3 argument, please feel free to send an email. So now everything I talked about was just sort of was about some very particular algorithm. It was about how well this semi-definite programming-based algorithm could yield sort of reasonable approximations to Sparsest Cut. So via a sequence of works, which is now, even now the slide is now outdated because it doesn't contain 30 papers, but there are some profound connections between these semi-definite programming gaps and actual complexity theoretic obstructions to solving the problems. There is some kind of mechanism to take a semi-definite programming gap and then convert it into an actual statement that the problem is difficult to solve by any efficient algorithm, assuming the unit games conjecture. But unfortunately, this connection is essentially unrealized for Sparsest Cut. So, at least in the context that I'm discussing here. So for instance, for this problem, the best thing that's known, even assuming unit games conjecture, is that there is no constant factor approximation. But so one hope would be that sort of this construction is now simple enough and has enough ingredients that look kind of like PCPs. It's instead of a global decoding, it's some kind of local decoding. You get somehow in PCP theory, you say if you have some nice property of some structure, then it has to be close to an algebraic, some kind of algebraic structure. And here you get the same thing, but now the closeness is only local. If you have some nice cut measure on this space, then locally it has to look algebraic, it has to look like half spaces. So the main open problem is whether you can sort of use this construction now to actually say something complexity theoretic about the Sparsest Cut problem. And I should just mention that the one thing that I'm working on here is algorithms for Sparsest Cut, but for small sets. So you want to find sets that don't expand, but you care about small sets and the relation to eigenvalues. And well, we can talk about it more offline if anyone's interested. But I'll end with that.
Further questions?
Of
for sparsest cut, the non-uniform version has some hardness, right? So uniform version doesn't.
So the non-uniform version has 1.001 hardness using.
Assuming UGC doesn't.
Not anymore, because basically there was some non-constant hardness, but that was before these algorithms that sort of said that it can't work in that regime. So it's not clear. It's not clear how like what the quantitative results are, like how fast you can let epsilon go to 0 and what the size of the label set should be. And in fact, the initial assumptions that gave growing hardness used some properties that don't seem to be true, given the algorithms. So, okay.
I guess all bets are off on everything you said if you allow additive slump in your.
Even like quasi-isometries.
Yeah. I mean, I can understand why in this situation.
For this purpose, quasi-isometry doesn't. I mean,
I can understand why here you would you care about points of zero distance.
But now this is a discrete proof. So actually, it also shows. I mean, there is a generic way to show it, but this also shows that this space is not quasi-symmetric to a subset of L1. As I said, you can in fact, instead of taking graphs sort of that have any infinitesimal structure, you can just take the one skeletons, and these distances are only grow. I mean, in fact, so you can take graphs where the minimum distance is 1. So then, quasi-symmetry and distortion are the same.
Right.
But oddly, the continuous structure is used fundamentally in the proof. So I mean, I don't know how to prove it on the skeletons. It just follows from a compactness argument. The skeletons essentially are isometric to nets in the continuous space. So by a compactness argument, since the continuous space doesn't embed, also the skeletons don't embed. But I don't know how to prove that directly.
So no more questions? Is that just again?